In this screencast, we are going to start looking at projectile motion. Projectile being an object that flies through the air, or is thrown, or is dropped. And we're going to be speaking about freefall objects, objects undergoing freefall, which means they are simply dropped. As we can see in this depiction here, there's a person standing on the edge of the cliff, and they just drop an object. This is free fall. The ball that she drops is free falling. So what is the behavior of an object when it undergoes free fall? Well, the first thing that you read about already with Galileo is that it undergoes uniform acceleration. That means it is constant. It also then means that the suvat and the shuvat equations all work. For something to undergo uniform acceleration, it means that the speed or velocity changes at a constant rate. In other words, the meters per second, the number of meters per second, every second is a constant number. In this case, for gravity, it's about 10. So we can see here depicted this object is being dropped. Initially it has a velocity of 0, and after 1 second its speed is approximately 10, after 2 seconds 20, after 3 seconds 30, 4 seconds 40, 5 seconds 50, 6 seconds 60. The rate of increase is 10 meters per second every 1 second. So in this 1 second interval, and every 1 second interval, the speed changes by 10 meters per second. That is the nature of free fall behavior, when something undergoes acceleration caused by gravity. That's free fall. So the value of g, what is g? G is a quantity known as the acceleration caused by gravity. This is the value, g. These are the values, g over here we use. At sea level, on Earth. At every other location in the universe, the value of g is a different number. But at sea level, on Earth, this is the value. We're going to study the nature of g in greater depth a little later in the course. But what this means is technically that if we go to the moon, gravity acceleration is different. On Jupiter, it's different. It also turns out that if we go very far away from the surface of the Earth at sea level, g will also be very different. So that leads people to sometimes think, well then if I go up in an airplane, is g different? Theoretically, yes, but practically no. And the reason for that is, although it seems high to us at our scale, gravity doesn't change that much between the surface of the Earth and the height that an airplane travels, which is higher than the tallest mountains on Earth. So let's take a look at these values in a little more detail. Out to 6 significant digits, we have 9.80655 meters per second. 3 significant digits, 9.81. And that's just this number rounded to 3 significant digits. We would use either of these two values whenever we use a calculator. very frequently you'll see in textbooks and people talk and teachers and demonstrations use the value of 10, just as we saw in the previous example, 10 meters per second squared. Well, that is simply 9.81 rounded to the nearest one, which would be 10. We do this for quick calculations or when we do it in our heads. When we are looking for almost an order of magnitude estimate. As you can see, as we go in this direction, the precision increases. So we can get a value. So these are the values of G. So let's now, when we approach a problem of free fall, consider and apply our knowledge of reference frames. If we have a coordinate system, we could consider, say, if this ball that's being dropped in this picture, what's actually being depicted here is there's a flashing light that goes off periodically. Most of us now have an app on our phones that allows it to be used as a flashlight, and you can control the blinking rate. So what's happening here is there's a long-term exposure picture being taken, and the flash, or there's a light that's flashing a certain number of times per second, but one picture is taken as the ball falls. And what you can observe, just like we observed in that first cartoon picture, is that with each successive interval of time, the ball is traveling further, which means that its average speed is greater. So we see the average speed is increasing because the distance between the objects is increasing. So now in terms of describing its position or its displacement or even its velocity, we could look at the reference frames. We could set up a reference frame where we're saying the bottom is 0 and say the drop height is 100 centimeters. Or we could say the release height is 0 and the bottom is minus 100 centimeters. We can use both of them in this situation. This has some implications for the equations we'll draw, that we'll create. So the first one we'll have here is we'll do our velocity equation first. And we have velocity equals at plus v0. Well, the velocity at any given time is given by this equation. And the acceleration is in this direction. It's getting faster in this direction, the negative. So the velocity then is negative 10 t. And the initial velocity is 0. Over here, we can see that the velocity is also at plus v0. The acceleration is also in this direction, so it is still negative 10t plus v0. So the equations are, and the initial velocity is 0. So we have the equation negative 10t. So it has no effect whatsoever on the velocity equations. Now when we consider the position equations, we have x equals 1/2 at squared plus v0t plus xo. 1/2 the acceleration is 1/2 of negative 10 t squared. The initial velocity, since it's being dropped, is 0. We have 0t, and the initial position in this case is 100. So that leaves us with x equals negative 5t squared plus 100. Now this is what we would call the model. The mathematical model that describes the position of this object. Over here, if we do the same thing, we have x equals 1/2 at squared plus v0t plus xo. X is 1/2 negative 10. Initial velocity is again 0, but the initial position in this case is 0. So setting up the coordinate system this way yields negative 5t squared. So if you notice, the model here is far simpler than the model here. The velocities are the same. So if all we're going to do is analyze the motion of this, we have a simpler equation in this particular case. So that can give us an advantage. Now it's time for us to take a look at the behavior of these free-falling objects. In the previous example, we considered two different reference frames. So what do the speed and velocity and position and displacement graphs look like from these two different reference frames? So we'll call this one reference frame A and reference frame B. These graphs will be speed graphs. And this will be time. Now the first thing we want to ask ourselves is what can we read from these graphs? And what we can read is speed and time. The gradient or the slope gives us the acceleration, and the area gives us the distance because we're dealing with speed. So let us consider what happens at time 0 in reference frame A. In reference frame A, at time 0, at the instant after release, that's what we mean by time 0, is it's the instant it's released. So it's being held in the hand, it's the instant that the pressure is released. That instant in time is so small that nothing has yet occurred. So the speed is still 0. And what we know then happens to the speed is the speed increases at a constant rate. So it's say 1 second, 2 seconds, 3 seconds, 4 seconds, 5, 6, 7. And we know that that rate of increase is 10 meters per second every second. So we start with an initial speed of 0, and after 1 second, it's 10 meters per second. 2 seconds is 20 meters per second. 3 seconds, 30. 4 seconds, 40. 5 seconds, 50. So that's what the speed graph looks like in reference frame A. Now again, if we go back to what we can read the speed and time. So at 3.5 seconds, we could read this off and say 10, 20, 30, 40. So at 3.5 seconds, we could read off 35 meters per second. The gradient is the acceleration. The slope of this is 10 over 1. 10 meters per second every 1 second. And that slope remains constant. The area is the distance. And that distance would be given by 1/2 AT squared, which we've seen before. Now let us consider reference frame 2. We have the object here at the top, and it's about to be released. At time 0, the speed is 0, and the speed increases at a constant rate of 10 meters per second every second. So after 1 second, 2 seconds, 3 seconds, 4 seconds, you'll observe that the graph is exactly the same. 0, after 1 second, it's 10, 2 is 20, 30, 40, 50. So both of these reference frames, the speed time graphs will look exactly the same. Now let's ask ourselves if that is true of the velocity time graphs. So now we will move down to these coordinates. We have velocity and velocity, time, time. What can we read off these graphs? What we can read is the velocity and the time. Put the little arrow over it indicating it's velocity as opposed to speed. The gradient, of course, is the acceleration, and the area now is the displacement. label our times. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So now let us go back to reference frame A. Reference frame A, we said that the velocity is given by negative 10t. So at time 0, the velocity is 0. At time 1, the velocity is negative 10. At time 2, the velocity is negative 10, 20. Time 3, the velocity is negative 30. So in contrast to the other graph, the speed graph, at time 0, the velocity is indeed 0, but after 1 second, it's minus 10, minus 20, minus 30, minus 40, minus 50. So we can read the velocity in time. We go to 2.5 seconds. We come down to the curve. We can read negative 25. That will be the velocity. The acceleration is the gradient. And the gradient in this case is negative 10. Every 1 second, the velocity changes by minus 10, and it's constant acceleration. And the displacement, of course, would be the area. Now, the curious thing in this case is we frequently talk about the area under the curve, but really what we're looking at here is the area between the x-axis and the curve. So the area in this case would be here. And it turns out this will give us a negative area. Things that are below the x-axis will be a negative area. Areas above will be positive. And we'll see how that plays out later. So that is in reference frame A. Let us consider reference frame B. In reference frame B, we again have a negative directed velocity, and it's increasing. And we saw that the model for velocity is also minus 10t. So that graph will look exactly the same as well. So whereas the velocity graphs, it makes no difference which reference frame we look at, they will be the same for that particular object. And by reference frame, I mean where we set 0. These will look exactly the same, the velocity time graphs. And the speed time graphs will look exactly the same, but they will look different from each other, and that's because speed is not a vector. It will never be negative. In this next segment, we'll now consider distance, displacement, and position graphs, and look at those accordingly. And the two different reference frames. So we will again consider this to be reference frame A, this reference frame B. We will first look at the distance. And we can ask ourselves, what is it we can read from a distance time graph? We can read the distance and the time. The slope gives us d over t, which is the velocity, or the speed, excuse me. And the area is distance times time, which is meters times seconds. Meter seconds means nothing. So in this particular case, a distance time graph means the area gives us nothing of consequence. So now let us go back to our situation. What we can see in reference frame A is at time 0, the distance is 0. But with each increment of time, the distance itself is increasing. So in the same interval of time, the distance is increasing. So we start with a distance of 0 at time 0, and the distance in the first interval of time is a certain amount, the change in distance, represented by that. In the next interval of time, the distance covered will be greater. And in the next interval of time, the distance will be greater still. And in the next interval of time, the distance will be greater still. So what we see is a curve, which is a parabola. Now what's interesting is, we can read the distance and time if we have numbers off the graph. The slope, or the gradient, gives us the speed. The speed would be given as a tangent to that point, at any point on the curve. Now what we said previously is the speed is increasing, and if you notice, the gradient of this curve is increasing with each successive interval of time. As time passes, the gradient increases. And notice I put an S here. This should be G for gradient. Now let us consider time reference frame B. What do we see? In the beginning, the distance traveled is small, and with each increment, the distance increases again. So just like we saw with the speed time graph, the distance time graph for those two reference frames look the same. So the reference frames don't matter in this particular case for the distance traveled. So now let us next go to position and examine the position time curves. So we'll have position time, which I will display in red. And what is it that we can read off a position time graph? Well, position time graph, we can read position and time. The gradient is the velocity with a vector over it. And the area gives us nothing. Again, it's meters seconds. So we'll have position. Going back to our reference frame in A, we can see that at time 0, the position is actually 100. The position is actually at 100. And it decreases a little bit, and with each successive time, it decreases even more. When we look at our model for this, what we see is x equals negative 5t squared plus 100. This plus 100 is an intercept. And we can see this is a parabola, and it's a downward cut parabola because of the negative. So, in this curve, for the position, which we will plot in x, we start out at a value of 100. And in the first increment of time, the position doesn't change very much. But in the next increment of time, it changes more, and the next increment of time even more, and even more still with the next increment of time. And what we said in looking at that function is that appears to be a negative cupped parabola. So we can read values. We could have a particular time over here, and at a particular time, we could read the value of the position off the curve, x and t. The gradient we said is the velocity. Let's examine that. The velocity is the gradient, which is given as the tangent of the curve. And if you see, as time progresses, the gradient, or the tangent, the slope of the tangent, at any point is increasing. And at the very beginning, you can see the tangent is actually, slope of the tangent is actually 0. So that makes sense. Now the area also gives us nothing. So that is from reference frame A. Reference frame A, again, is where we set the top at 100. Reference frame B, we made 0. So notice now the ball is going to travel from an initial position of 100 to negative 100 and follow the same kind of pattern. And when we look at the model, we see it's x equals negative 5t squared. Well, what is the difference between these two models? It's this intercept. The intercept is different. In this case, the intercept is 0. In this case, the intercept is 100. So all that will occur in our graph is this curve to be shifted downward. So we have 0 and we have minus 100. Very little distance change in the first interval, more in the second interval, quite a bit more in the third, and even more still in the fourth. Our curve looks like so. Again, a negative shifted parabola, the only difference being the intercept. Now, we can read x and t the same way. We have a time, we can come down, and we can read a position. The velocity is given by the gradient of the tangent, and you can see that that slope is, or gradient is increasing, and that in both graphs, the gradient is negative, which means the velocity is negative. It's headed toward negative positions. So again, referring back to the models, the only difference here, we're switching reference frames, is whether we have this intercept to deal with. Now it turns out in certain cases, this will be easier to deal with mathematically and solve than this one. So in simple cases, this advantage of setting the initial position equal to 0 can have advantages. It can simplify calculations. But there are advantages, as we will see later in the course, for using this particular reference frame in terms of the mathematics. So let's do our first problem. So here's a word problem we might deal with. Blake is standing at the top of the World Trade Tower and drops a pebble from the top. Of course, that could be rather dangerous, but this is a theoretical exercise. When will it reach the bottom, and what will its velocity be? So let's learn a little bit about the World Trade Tower. This is a diagram I found of the tallest 20 buildings in the year 2020, because one of them is still under construction, the tallest. Below them, I have a list. World Trade Center. We're familiar with the World Trade Center. So that's the 12th tallest building in 2020. It's 1776 feet tall, no coincidence. That's the year of the Declaration of Independence. That was intentional. So that is the World Trade Tower right there, number 12. Now when you look at it in comparison to all these other buildings, you can see that the main floors stop here, and then it's a tower the rest of the way. When you compare it to this next one, you would say, wow, this building's a lot bigger than this one, even though they seem to be close in height. It seems to almost be one way that people cheat to make their buildings taller is to put radio antennas and so forth at the top. And let's suppose in this case that Blake is able to actually get to the very, very top and stand there. So this is the World Trade Tower. The next building is the Doha Convention Center, located in Doha, Qatar. It's 1,800 feet, so it's about 30 feet taller. The next one is the Rote World Tower in Seoul, Korea, at 1,819 feet, so about 40 feet taller. But again, when you look at the size, much more massive building than a World Trade Tower. And then we go to the 9th tallest building, the Golden Finance Building in Tianjin, China, which is this building here. And you could see, again, substantial building and quite a bit taller. And now we're talking about a building in 1957, almost 200 feet taller. The next building is just an unbelievably massive building when you look at its scale. It's the Mecca Royal Tower Hotel in the Mecca region of Saudi Arabia, near the city of Mecca and the religious sites there. And you can see there's the top here, and you've got the crescent and the moon at the top. And it is just a little bit taller, about 15 feet taller than the Golden Finance Building. Then we have the Wuhan Greenland Center in Wuhan, China, in 1988 feet. So about a little over 200 feet taller than the World Trade Tower. Then we get to the Shanghai Tower in Shanghai, China, 2,073 feet, a full 300 feet taller. And then we get to the Signature Tower in Jakarta, Indonesia. Very big building, but again, kind of pointy at the top rather than having floors at the top. And then we have the fourth building, the Seoul Light DMC Tower at 2,100 feet, just about the same height. But again, a tower getting up, a radio tower getting up there to the height of the other building. Then we get to the Ping An Finance Center in Shenzhen, China at 2,165 feet. So now we're at a full 400 feet taller than the World Trade Center, almost 25% taller. 2,165 feet, the next building, the Burj Khalifa in Dubai in the United Emirates, is 2,717 feet tall. Now you may have seen this building in one of the Mission Impossible movies. It was featured there. This building is almost 1,000 feet taller than the World Trade Center. Almost 1,000 feet taller. And under construction is the Kingdom Tower in Jeddah, Saudi Arabia, also in the Mecca region of Saudi Arabia. It's 3,280 feet tall. It is almost 2 times or twice the height of the World Trade Tower. World Trade Tower would put it at about 3,500, so just about 200 feet shy of being twice as tall as the World Trade Center. And now when we step back and look at the magnitude and the massiveness of all of these buildings, the biggest one that we see, of course, in our skyline is the World Trade Center. And it's amazing to see these buildings throughout the world that are so much taller and larger and more massive than the largest ones we have here in New York City. So I just thought I would share that. So we have one World Trade Center at 1,776 feet, 541 meters tall. So in beginning this problem, there's a number of steps we should take. First one is to draw a kind of a picture and create a coordinate system. So over here on the side, I'll draw the World Trade Tower like this, like so. And we know it is 541 meters tall. That's given to us. And Blake is at the top, and he drops it. So we're going to get this phenomenon, just like we saw previously. So our coordinate system is set up in this direction, in the vertical direction. And so we might call it y. The y direction is 541 meters. So now the question is, when do we want this, where do we want this to be? Now there's where do we want our coordinate system to be set up? Where do we want the 0? In the previous example we saw it can be useful to make the 0 at the top for the position. So if we make the top 0, and this then negative 541, we may get a simpler equation. So let's examine this as a possibility and write out our equations. First we'll do our velocity equation. The velocity is equal to at plus v0, and the acceleration we know is negative 9.81 t. Now if you recall, when we're going to pull out our calculator, we'll use more specific values, negative 9.81 or negative 9.80655. The initial velocity is actually 0 because he's releasing it from his hand at rest. So this is the model for the velocity. Now let us consider the model for the position. Y equals 1/2 at squared plus v0t plus y0. It's y0. So now we have y equals 1/2 of negative 9.81 t squared. The initial velocity is 0, so this term drops out, and the initial position we set is 0. So we are left with y equals negative 4.905 t squared. So that's the model that describes our position. So now the two questions we're being asked to answer are, when will it actually hit the ground? Well, when it hits the ground, it will be located here at a position of negative 541. and what's its velocity upon impact. So we can actually just substitute in negative 541 equals negative 4.905 t squared. And then t squared is negative 541 over negative 4.905. And we divide that out. We get a time of 110.29562 seconds. Now, if we go back and look at our significant digits, we have 3 here, and we have 3 here, so our answer is going to be actually just 110 seconds. And we would write it as 1.10 times 10 to the 2 seconds is the time. So that is the time it will take for impact. Almost 2 minutes for it to hit the ground. Now when we look at the velocity, since we have this time, we have v equals negative 9.81 times 110.29, the unrounded value. So we get a velocity of negative 1,082 meters per second, which we can use 3 significant digits, so it's 1.08. So we want to go to scientific notation right away. It's going to be negative 1.08 times 10 to the 3rd meters per second. Boxed answer. So that's how we would solve this by hand. What do the graphs look like, the velocity and the time graphs? Let's examine these next. Velocity time is negative 0.91 t. That's a linear function with a slope of minus 10. So we're beginning the velocity is 0, and it will look like this. So we see it increasing rapidly and rapidly and rapidly. Over here, we have our yt. Now, in our coordinate system, we started at 0, and it's going to end up at minus 541. And our model, which is negative 0.4905 t squared, is a downward cupped parabola. So it looks like this. So to start this problem by hand, the first thing we need to do is to set up a coordinate system. So we have a building that we know is 541 meters tall. And we could set up our coordinate system like this, so that this is 0, and that would make this negative 541. And this would be our y coordinates. So our first equation we would set up as our velocity equation. V equals at plus v0. Our acceleration is downward in this coordinate system. It's getting faster in this direction, so it's negative 9.81 t. And we use 9.81. We wouldn't use 10 in this case because we're going to be pulling out our calculators to do this. So whenever we use our calculators, we're not going to use 10. Initial velocity, since it's dropped from rest, is 0. So we have our model for the velocity, which is negative 9.81 t. Moving on to the position, we have y equals 1/2 at squared plus v0t plus y0. So we're dealing with the vertical. And we have y equals 1/2 negative 9.81 t squared. The initial velocity is 0. So this term drops out. And that leaves us with the position of y0, which we said is 0. So that just gives us a model of negative 4.905 t squared. That's our model. So if we want to find the velocity at impact, so we have these, before we do any solving, we want to graph these so we can have a sense of what our answer will be ahead of time. So we have velocity and time, like so. And our velocity, we know, starts at 0. That's the easy part. It's drop from rest. It starts from 0. But we can see it has a negative slope, a negative 10 slope. So it's going to look like this. Acceleration is negative 9.81. Again, we can read velocity and time. The gradient is the acceleration, and the area is the displacement, delta x. So that's what the velocity time graph looks like. When we look at the position time graph, our model is a downward, it's a negative 4.905 t squared. So it's got a negative coefficient, which means it's downward cup, and it's a parabola. When time is 0, y is 0. So we have a downward cup parabola that looks like this in that coordinate system. So that's what we expect to happen with the function. So now, what about impact? At impact, if we're looking for the velocity, we don't know the time, nor do we know the velocity. We're not given the impact velocity. We don't know how long it takes. In the y position, we don't know how long it takes, but if we look at our diagram, we know at impact, its position will be negative 541. So negative 541 goes here for y, that's what y will be, equals negative 4.905 t squared. So then dividing on both sides, we get t squared equals negative 541 divided by negative 4.905. And then we find out that t squared is equal to 110.29562. So then t is the square root of that number. And the square root of that number is 10.47363. So we would say the time, now we need to worry about significant digits. We had 9.81 here was the time we used, 541, each of those had 3. So we're looking at a 10.4 place, but that's a 7. So we would say the time is 10.5 seconds. And that would be our boxed answer for the time. So it would take 10.5 seconds to fall from the very, very top to the ground, that pebble. Now what would the velocity upon impact be? That is v equals negative 9.81 times 10.47363. And that will give us an answer of 10,000. I made a mistake. 102.7463 meters per second. Now again, we have 3 significant digits with a 9.81, and this time really should be, this answer should be relegated to 3 significant digits. So the third place is the 2, so we would say the velocity is 103 meters per second. And then in scientific notation, 1.03 times 10 to the second meters per second. So that would be our final answer. It'll take 10.5 seconds, and the final velocity will be 100 meters per second. Very quick. So now we might ask, what would have happened if we had set up our coordinate system the other way? What would have transpired? Well, we still have our building. It's 541 meters tall. And now how we would set this up differently is to make this 0 and this 541. When we consider the velocity equation, we have v equals at plus v0. Acceleration is negative 9.81, and the initial velocity is 0. So we have a model for the velocity that's exactly the same. The reference frame has no effect on the velocity. And now when we look at the position, we have y equals 1/2 at squared plus v0t plus y0, negative 9.81 over 2t squared plus v0t, and the y0 in this case is 541. Now this v0t team, since v0 is 0, this term drops out. So we're left with y equals negative 4.905 t squared plus 541. So the velocity model looks exactly the same. The position model, however, do not look the same. Yeah, that's what we varied. So now we could set about solving this. Upon impact, the position will be 0. So we substitute in 0 for y, and we get negative 4.905 t squared plus 541. Solving for t, we're going to subtract 541 from both sides, and we get negative 541 equals negative 4.905 t squared. T squared then would be equal to negative 541 over negative 4.905. And if you notice, that's exactly what we have over here. So for this particular case, what we can see is it makes no difference in the velocity model. It does make a difference in the position model, but in terms of the mathematics involved, it ultimately makes no difference. It's not any more complicated to set it up that way. The next way we can look at this problem is to use our spreadsheets, like an Excel, to study this problem. And we can get some answers very quickly once we've written models. We have our time in seconds, we have our velocity in meters per second, and we have our position in meters. Now let's say we use a 1 second increment, so we have 0, and we'll go by 1 second, so equals this cell plus 1. And our velocity model was negative, and let's in this case use the 6 significant digits, negative 9.80655 divided by 2 times t squared times time, which is over here, and that was our velocity. Oh, whoops, I put it in the wrong place. Our velocity was simply equals negative 9.80655 times the time. And our position now was negative 9.80655 divided by 2 times t squared and we fill these down one, and we then fill downward. Let me format these cells so they look good, consistent, easy to see. Didn't fill the times down properly. There we go. So we go from 0 to 10 seconds, and we'll go to 11 seconds. And what we can see, the position, the height of the building would be negative 541, which would occur between 10 and 11. And the speed, which we calculated to be 103 meters per second, is between the 98 and 107. Now here's what's kind of interesting is we can insert some rows here. Or we can just make this go by 0.1 to get a better resolution. And now we've gone past 11 seconds. We can use this and fill down and get better resolution on this. So we can see we hit 103 at 10.5 seconds, and this would round to 541, the height of the building. So we can actually confirm the values here. So the spreadsheet modeling, once we have a model for how the thing behaves, it becomes very quick and easy and powerful to model the function. And of course, we already know how to make graphs, so I won't go into the detail of making the graphs on Excel. So for this World Trade Center problem, we've solved it by hand. We've looked at it in spreadsheets, and now the tool we'll have available to us on the IB exam and in exams, of course, is the graphing calculator. So how would we go about doing this? Well, the first thing we would do is we would go to y equals, and we would put in our velocity equation. And our velocity equation was negative 9.80655 x. Now if we wanted to look at those values, we can go to second table, and here are the values at 1 second intervals. If we want to change the table, we go to second window, which is table set. We could start by 0 and go in the table by 0.1s. And then go back to the table, and we can see the speeds in 1/10 of a second intervals. So now I can go back to my y equals, since we didn't start there. Start with the velocity. We need to get the position first to find the time. I will turn the velocity off and put the position in. And that was make sure I turn that on. And that was negative, oops, parentheses, negative, negative 9.806 divided by 2 times t squared x squared, and we set the initial position at 0. But in this case, if you remember, both velocities models were the same. So in this case, I'll model the other one, plus 540, where we said it started at a height of 541. And now let's take a look at our table. And we see that it starts out at 539 and it's decreasing. And if we scroll down the list, we could find out when its height is 0. And we can see it's somewhere between 10.5 and 10.6 seconds. If go back and turn the velocity on, which I could have left on all the time. We can see that the velocity is between 103 and 109. The beautiful thing about this table is I can set it here like so, around 10.5. We know it's more than 10.5 seconds. I can go back to the table set and make this 0.01 seconds. Then go back to the table. And find that location where we have 0 and the velocity. So we can see to this decimal place now, we're between 103 and 103.1 meters per second. The height would be 0. And it's about right in the middle, so like 103.05. And we had 102.74 when we used 9.81. So, but we still, to the level of precision of of 3 significant digits, 103, we were right on the mark there. But this is how we could get increasing levels of precision. Yet another simple and powerful technique for solving this type of problems comes from the equation that we know is always true, that the displacement, delta x, is always equal to the average velocity multiplied by the time. The displacement is always equal to the average velocity multiplied by the time. So let's consider the case of this same problem. Let's consider the case of the free fall. We have our time column here. We have our velocity. Well, from the moment it's dropped, we have a velocity of 0, then negative 10, negative 20, negative 30, negative 40, negative 50, negative 60, negative 70, negative 80, negative 90, negative 100, and negative 110. Now I knew to stop here because we know the velocity impact velocity is about a negative 103. So the question is, what is the average velocity? Well, we don't really have an average velocity at time 0. So that cell is blocked out, like so. But the average velocity during this interval now is 0 to minus 10. The average velocity is minus 5. Now, from the beginning to the end of time 3, from 0 to 20, the average velocity is minus 10. From here to here, the average velocity is minus 15. From here to here, the average velocity is minus 20. So after 6 seconds, the average velocity is minus 25. 7, it's minus 30. 8, it's minus 35. Minus 40, minus 45, minus 50, minus 55. Because this is our example starting from rest, it is the case that this average happens to be 1/2 this. But that's not a rule to memorize. It's the total, the average velocity is the initial and the final averaged. It won't always be that case. You can see that if it doesn't start at 0, then this won't be a pattern. So don't look at this or remember this to be a pattern of it's always half. So now displacement is average velocity. Displacement is average velocity times the time. Well, all of these times are off actually in the table. This should be 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So at time 0, the velocity was 0. At time 1, the velocity is minus 10. So those calculations are correct. But we don't have any displacement, so we could say the displacement we know at the beginning is 0. But the average velocity is minus 5 times 1 means minus 5. So the displacement is negative 5 meters. After 2 seconds, it's minus 20. After 3, it's minus 45. After 4, minus 80. After 5, minus 125. After 6, minus 180. After 7, minus 245. After 8, minus 320. After 9, 405. This minus 500. And here we have minus 550. So we could see then that the impact time would be between 10 and 11 seconds, because we have 541 as the target, and that the impact speed would be 100 and 110. This is a very, very fast way to evaluate an object undergoing acceleration. I like to use it in free fall because there's some other cases for it. But this is a very powerful technique. Very quick and simple. Most problems are much shorter, only over the first few seconds. So this can be a very quick and dirty way to solve one of those problems. Last but not least, I want to talk about free fall and air resistance. So far, we have assumed something. We have made the assumption and you know the old famous saying, when you assume, in science, when you assume it's not necessarily true, but it is some place for us to start. So we assume 0 air resistance, which will not be the case anywhere except in outer space or on the moon or some place like this. So here what we see here is we have a Navy SEAL diving, free falling, skydiving, and he just looks like a normal person. If underneath this you had what looked like a carpet, it would look like he was just lying on the ground. But instead he is actually free falling from an airplane. And what happens with free fall, as you go faster and faster, you are impacting and hitting ever-increasing numbers of air molecules. And every time they impact you, they are pushing upwards. They're pushing upwards. So that's what happens. So what that serves to do when the air molecules are resisting is it tends to reduce the acceleration caused by gravity. Here we have another image of a housing development in Dubai. You may have seen this made in the image of a palm tree. They built these islands and a whole bunch of homes. We have a group of skydivers here. Well, how does this air resistance or force of air resistance behave? The force of air resistance is proportional to the velocity squared. This alpha means is proportional to. Another way of saying there is a constant of proportionality. So saying force is proportional to v squared is the same thing as saying is F equals kv squared, where this is the constant of proportionality. So we said that the effect of air resistance is to reduce the acceleration caused by gravity. Well, that force of air resistance that reduces the acceleration increases as you go faster. It's important for us to remember in this course that that force of air resistance is proportional to the velocity squared. So when this velocity is small, the force is small, the force of air resistance. But as this gets bigger, it has a disproportionate effect on the air resistance. So what happens with a skydiver is as one goes faster and faster, one comes into contact with ever greater numbers of air molecules that provide greater and greater force of resistance. And there comes this point where there is the force of gravity pulling you downward and the force of air resistance are equal to each other. And once that happens, we have reached something called terminal velocity. A velocity at which the velocity remains constant. The acceleration equals 0. So let us take a look at a graph. A velocity time graph of an object undergoing free fall. So we know it undergoes free fall, its initial velocity is 0. And then we say in the first second, its speed will increase by 10 meters per second. And in the second, it will increase, it wants to increase by another 10 meters per second, but there'll be a little bit of air resistance. So what I'm going to do is draw this line, which is how it should behave. But what actually starts to happen as the speed picks up is the air resistance starts to have an ever greater and greater effect until eventually the resistance remains constant. So the resistance increases, but the velocity remains constant. So you notice here the velocity, we've now reached an asymptote. And that asymptote is the terminal velocity. And you can see there's this kind of curvature here, and that is related to the velocity squared. When we study forces a little bit later in the course, we will get into much more detail about this, but this is the nature of free fall, air resistance, and terminal velocity.